cycle. This is a example of a gas turbine that it was, what is a Siemens Westinghouse gas turbine. Let's just go through the numbered systems. So one is the inlet section. Usually the air comes down and then it'll come around. You can see the cutaway, and then it goes into the compressor section. So number 2 is a compressor section. Often it has multiple stages of stators and rotors, rotating blades. It catches it, turns it with an angle, catches it, turns it back. In fluid mechanics, sometimes you wonder, why are we studying vanes so much? And you have a jet of fluid hitting a vane. Well, this is why. That's what's happening. Even though it's axial flow going this way, it's always changing back and forth. Okay. Then once it goes through the compressor section, then you have fuel added to it in a combustion section. Often there's a number of cans that go around in a ring. Now you have a hot, high pressure exhaust gases. You pass it through a gas turbine section. It's often fewer stages, but the same concept of the compressor, having stators and rotor blades. You're going to pass it through there, and it'll then generate mechanical power in a shaft, and that shaft is connected back to the compressor. So that's how the compressors run. It's on a shaft. And if there's excess power, well, then you come out to this flanged interface right here, which you would then hook up to something. Here, if you're making electricity, you hook it up to an electric generator. And now the rest of the, all of the products of combustion, then you would drop it to the lowest pressure possible. Typically, you have a little diffuser so that you can get the lowest pressure at the exit of the last turbine stage. There'll be a little pressure recovery, and then you exhaust the gases out. That's a gas turbine. So what are the major components of this gas turbine? Well, the first one was the compressor. What's the object of the compressor? To get P2 much greater than P1. And this is a very difficult tongue twister for us. Coming off of the Otto and diesel, we learned about the compression ratio. You would think that the compressor would specify a compression ratio, but it doesn't. What is specified for the compressor is the pressure ratio. So the pressure ratio would be P2 over P1, and maybe that's 9 or 8 or 17 or 12. It's not V2 over V1. That is not specified for gas power cycles. The pressure ratio is what's specified. So the ratio P2 over P1. Now you go through the burner or combustor, different names for it. Here you're actually adding the fuel, and you're coming out with the temperature much greater than the inlet temperature to the combustor. What about the pressure difference going through the combustor? The same. All right. In actuality, you have some pressure losses, but those are minor. We're only looking at the major pressure gains across the compressor, and then loss or drop across the turbine. So the assumption is P3 is the same as P2. And then the last would be the gas turbine, and then these pressure at 4 is about the same as the pressure back at 1. And then you have now the products of combustion, they have to be exhausted. So the real gas turbine does have the compressor, the combustor, and the turbine. Well, we want to simplify it so we can analyze it. So we have the air standard Brayton cycle. So it always behaves as air. There's no products of combustion, 100% air all the way through. It's an ideal gas, so there's 3 things. PV is equal to RT, U is a function of temperature only, and H is a function of temperature only when we talk about an ideal gas. The combustion process is so complex, but we just replace it with a heat transfer. Often we'll put Q in. That's the way I'll write it, Q in, or Q combustor, or Q burner, something like that. Then you have the The exhaust and the intake, well, that's complicated. We want to close the loop, so you put a heat exchanger in there, and then you have a Q out. So either you'll have a positive Q out, or you'll have a negative QHX. How's that? You'll see me do it both ways. Either when we do a control volume analysis around this heat exchanger, you have to pay attention. I know that's heat out of that heat exchanger, so if I stay with the sign convention for Q in is positive, it'll be a negative Q for that heat exchanger. All right. If you have the additional cold air standard analysis of the Brayton cycle, it's everything above. It's air, ideal gas, combustion's replaced by heat transfer, and intake exhaust is replaced by heat transfer. Plus you have that you use constant specific heats. That's the cold air. Constant specific heats at 298 Kelvin, 25 degrees C. So what do? We have a control volume around each of these components, and then we can analyze the primary heat or work transfers for each of those components and then do a cycle analysis. We have used these equations for isentropic flow for an ideal gas, constant specific heats. We use these two right here for the auto and the diesel. And we didn't really use that one, but now we use it because the pressure ratio is what's specified for the Brayton. So the Brayton cycle. So when you're given a problem like this, these are the steps that are very similar to the steps for the auto and the diesel, actually the steps for the Rankine cycle as well, for vapor power. What do you want to sketch first? And all the major components of that cycle. And then you want to introduce labels where the states are. Label each state. And so it's not that hard for our system. What did we have? Compressor, a burner or combustor, a gas turbine, then some heat exchanger. Those would be the four major components. And then it's conventional to put inlet state 1, then state 2, then state 3, then state 4 closes the cycle. You want to go ahead and sketch a diagram. It helps you organize, like what's happening between here. A very useful diagram is the temperature entropy diagram. Now, when you analyze this system, you really only have the high pressure side and the low pressure side, because isn't P1 and P4 the same? Yeah, and P2 and P3 are the same. So that really helps us when you sketch a temperature entropy diagram. I know that we don't have any phase change. A lot of people want to put the dome on there, but if it's ideal gas, it's far away from the dome. If you wanted to, you could put the dome right down here. There's the dome, stay far away from it. Okay. And then you put a line of high pressure and a line of low pressure. And we're going to start at the low pressure, low temperature, state 1. And we're going to compress and get up to that high pressure line, state 2. Well, if that compressor, is there supposed to be any heat transfer with that in or out of that compressor? No. The standard assumption, it's primarily a work transfer device. Hence, it's internally reversible and it's adiabatic. Hence, it's isentropic, straight up to state 2 on a TS diagram. Then you constant pressure heating, so it goes up to some state 3. The temperature goes up along that line of constant pressure on a TS diagram, there's state 3. And then you do the same thing through the turbine, isentropic expansion through the turbine, and then you have the heat rejection. There's the cycle. Once we have a good idea, we want to construct a table of properties at each of the states. The properties of interest are the pressure and the temperature. The pressure is really easy. There's only two values, high and low pressure, and you only have 4 states. 2 are at the low, 2 are at the high. That's pretty easy. The hard part is getting all those temperatures solved for. And so if you're interested, usually you're given T1 and P1. Those are often given. So how do I get T2? Well, we use that analytic expression. T1 times the ratio of pressures, P2 to P1 to the K minus 1 over K. What happens if I want to count for variable specific heats? Well, it's just like the Otto and diesel. I'm going to use that table A22, and I'm going to use PR column for isentropic compression. So you march around. When you go from 3 down to 4, is T4 equal to T3 times the pressure ratio is switched. It's not a number like 9 or 10 or 15 P2 over P1. It's just the opposite. It'll be the low pressure P4 divided by the high pressure P3 raised to the same exponent K minus 1 over K. True? Yeah. And you know, I'm going to use this in a second. I can replace P4 by P1, and I can replace P3 by P2 to the K minus 1 over K. T3 is equal to T4. All right. Once we have the table of all of our temperatures and pressures, and if you're doing variable specific heats, then you would want to get your PRs and your H's. Okay. But you want to then construct a table of all of our heat and work transfers. So this one's probably I'll just spend a little time on. So for each component, we're going to have either Q in kilojoules per kilogram or work in kilojoules per kilogram. And how many components do we have? Well, we have the compressor, we have the burner, we have the turbine, and then we have this heat exchanger. Now, there's 8 entries in this table, 4 of which are 0. Half the table is zeros. So for the compressor, is Q or work 0? Q. For the burner, the work is 0. Turbine, Q. Yeah, you see the pattern, pretty good. And then also, if we stay with our sign convention for each of these components, the compressor work is going to be negative, isn't it? Isn't it going to be negative? And then the burner heat transfer is going to be positive. The turbine work is going to be positive. And that heat exchanger heat transfers out of it, so it's going to be negative. And I didn't leave enough room, but if I do this, if I say the sum, doesn't this give me Q net? And this is work net? And are they going to be the same? They must be the same. They will be the same. Same if you use variable specific heats or if you use constant specific heats, either one. So once I have the Q's and the W's, I can now solve for the thermal efficiency. The thermal efficiency is exactly the work net. I can't write it. Work net divided by the Q in, which is only in the burner. True? All right. And the back work ratio will be what percent of what comes out of the turbine, work out of the turbine, that has to go back and feed the compressor. And because that's negative, we'll put a negative sign on it, so it's a positive back work ratio. You got it. That's the map. You can solve all these problems now. Just have to step through carefully to avoid errors. So for this problem, given that initial temperature and pressure, the pressure ratio, the compressor pressure ratio is 9. Oh, by the way, engineers have done a great job of steadily increasing that pressure ratio for real operating gas turbines. And it's inched up and inched up and inched up and inched up, and it's great for performance. And so 9 would be a pretty low value now, up around 20 for some very top-end, high-end gas turbines. And then the maximum temperature is given, and then you would just walk through the cycle. Let me do this. This is the solution for that problem. I know I do it in Excel, but you could see like organization of property information about the pressure ratio, 9. And then These were the inputs given. They're a little bolder. And then how did we get this pressure right here at 2? 810 kilopascal. Just pressure ratio times P1. Boom. And both of these are my high pressure, and this is both the low pressure, so the pressure column's easy. And then how do we get that T2? Well, that's T1 times P2 over P1 to the K minus 1 over K. Sometimes what I'll do is I'll get tired of doing K minus 1 over K, and I'll just put a column for K, and then I'll put another one, K minus 1 is so much, put that in an entry. Then I'll put K minus 1 over K is so much, and put that in another cell in Excel. Okay. And likewise, you do just the reciprocal to come down from state 3 to 4s. Here are the table of all of the heat transfers and work transfers. Why is there a per kilogram on these terms? Yeah, it's per unit kilogram that flows through the device. Would it be the same as the Q dot in the burner divided by the mass flow rate of air through the burner? Yeah, that's exactly what that lowercase q of the burner is. Okay, now we're solving it for constant specific heat, so we're going to use that C sub P. For this problem, you don't really ever use C sub V. There's really no change in internal energy that you need to calculate. Because for the burner, Q in the burner, isn't that going to be the enthalpy exiting the burner, which is state 3, minus the enthalpy coming in the burner, state 2, which is my constant specific heat, T3 minus T2, if you're using constant specific heats? Yeah, that's what it is. So you march through the system. Notice that this one definitely is negative. Work is not out of the compressor. It's into, like work is, the heat is not into the heat exchanger, but it's out. But when you sum them, you get a good check. So we get Q net is equal to work net. And here's our thermal efficiency and the back work ratio. If you just take a look, that's a very high thermal efficiency. Gas turbines are pretty efficient if they're built well. Your back work ratio is going to be a challenge. What was our typical back work ratio in a Rankine vapor power cycle? Less than 1%. Now we're like 35%. So if you have any slippage, any degradation, let's say your turbine isn't isentropic flow through the turbine, or the compressor's not 100% isentropic efficiency, it will seriously degrade the system. And you will get a much lower thermal efficiency, and the back work ratio will go up above the 35%. Now, we're going to derive this equation right here. I didn't derive the simple equation for the Otto cycle efficiency. I didn't derive it for the diesel, but I'm going to do it for the Brayton, okay? And basically, if you do one, you can see the pattern, it's replicated. But this very simple equation just says, give me the pressure ratio, give me the K, where usually it's air, so it's 1.4, and then this is the simple equation to get the thermal efficiency, assuming constant specific heats. And if you use this simple equation, you get 46.6% thermal efficiency for a 1.4 K and a 9 pressure ratio, and it agrees. Excellent agreement. So let's press forward. Let's go ahead and derive this equation for the thermal efficiency of the air standard Brayton cycle, assuming constant specific heats. Well, right away what I need to do is I need to sketch. I'm going to talk about the compressor, the burner, the turbine, and the heat exchanger. I know I'm just repeating everything, but I think it's pretty good to repeat it. So this is state 1, state 2, state 3, and state 4. And we know what the pressures are. Isn't P2 is equal to P3? That's a critical observation. And P1 is equal to P4. That's a critical observation. And if we're using constant specific heats, we know what is T2 divided by T1. That's my P2 over P1 to the K minus 1 over K, Likewise, I'm just repeating what we did, is what about T4 compared to T3? Isn't that the P4 divided by P3 to the K minus 1 over K, which is P4 is equal to P1, and P3 is equal to P2 to the K minus 1 over K. This is a critical observation right now. And you say, look at what happens if I take T4 divided by T3 and I multiply T2 divided by T1. Can you see what that is? Hopefully you see that. So this is equal to 1. Now, how are we going to derive this equation? Well, you start with what is the definition of the thermal efficiency? Isn't it work net of the cycle divided by Q in? Can we replace work net by Q net? So Q net divided by Q in is Q net equal to Q in, and I'm going to put a minus on the Q out divided by Q in. I know that this is a positive Q in right here, and this is a positive Q out right there. That's why I put a negative in front of that Q out. Does that look good? So now this thermal efficiency is 1 minus Q out divided by Q in. Some people said I could have started there. Yeah, you could have, probably, if you were. The textbook often jumps to that version for the thermal efficiency. You can see the form is starting to take shape. You have 1 minus something. Look at this, 1 minus something. So we're on the right track. Okay, so now let's go ahead and replace what is Q out in terms of our temperatures and our specific heat. Isn't it C sub P, T4 minus T1? Is that what Q out is? All right. And then C sub P for Q in, it'll be T3 minus, T3 minus T2. Can you cancel the specific heats? Looks great. Now you say to yourself, okay, well, I'm going to have 1 minus. I'm going to pull out T1 out of the numerator, and I'm going to pull T2 out of the denominator. And so in the numerator, we'll have T4 divided by T1 minus 1, and we'll have T3 divided by T2 minus 1. That doesn't seem like it's all that efficient, but I can replace what is this T1 over T2, right? So if we do that, we have 1 minus, and then we'll put it down here. We'll put P2 over P1 to the K minus 1 over K. And we're left with this T4 over T1 minus 1. I'm kind of writing it a little funny here. Divided by T3 over T2 minus 1. So what we do here is we say, divide by T3 multiplied by T3, didn't change anything. Then we'll put divide by T2 multiplied by T2. So we just expanded what T4 over T1 is, isn't it? And now you look and you say, aha, T4 over T3 times T2 over T1 is just 1. And so the whole numerator is exactly the same as the denominator. They're both the same. They're both equal. That ratio is 1. And so now the thermal efficiency is just 1 minus 1 over the high pressure over the low pressure, the pressure ratio to the K minus 1 over K. QED, what we set out to show, has been shown. It's a very simple relationship. So, what is the trend? Higher pressure ratio gives you better performance, higher thermal efficiency. That's why the engineers have struggled to improve it. Well, take the same problem, and instead of having reversible flow through the compressor and through that turbine, specify an isentropic efficiency for the compressor and an isentropic efficiency for the turbine, and resolve. It's not that much more challenging, is it? It's just more tedious, is it not? Well, let me kind of go through the solution. I like to analyze the compressor in a number of steps, just like the turbine in a number of steps. So first of all, I calculate the work, the minimum work required by the compressor to achieve that pressure ratio. And so that would be the work consumed by the compressor if it was isentropic flow. How do we get this value right here? Well, it's going to be C sub P times T2S minus T1, where T2S is T1 times the P2 over P1 to the K minus 1 over K. Just what we did before. You have the T2S. And so this would be the minimum work. Well, if you have an 83% isentropic efficiency, you're going to need more work. So you take that minimum work, divide by the efficiency, and that's the 317.3 kilojoules per kilogram. So if you want to find then, this is equal to C sub P T2 actual minus T1, and you can then solve for T2 actual is equal to T1 plus the W compressor actual divided by C sub P. You can actually just do it all in temperatures as well. Very similarly for the turbine, it's just that maybe you would have gotten nearly 750 kilojoules per kilogram out of the turbine. Because of the lower efficiency, you don't get 750, you get less. So sometimes you multiply by the efficiency for the turbine or divide by the efficiency like the compressor. Anyway, you get those temperatures in the actual state 4 and the actual state 2. It will change your Q's and your W's. And then what did it do to the thermal efficiency? Let it slide a little bit. It's lower. What did it do to the backwork ratio? Went up. Both are not desirable. Not desirable. Well, can you plot this on a TS diagram? Can you start with state 1 right down here at the low pressure and move up to the line of high pressure? And can you start from state 3 up here, it was like 1600 Kelvin, and go to a line of low pressure for state 4? So can you show me, I'm going to pause and walk around, where state 2S is, as well as 2, sometimes I'll say 2 actual. Likewise, where state 4S is, as well as 4 actual on this TS diagram. So a lot of you have it, which is good. This is a temperature diagram. This is the entropy diagram. A lot of people knew right away that they go straight up to get to 2S. Right there would be 2S, right? But then they have to think for a little bit. Where is 2 actual? Well, think about, you have an increase in entropy, do you not, because of irreversibilities? So that points you in the right direction. So it'll be kicked up to this side. There will be the 2 actual. What about the temperature? The temperature 2 actual will actually be a little hotter coming out of the compressor than if it would have been reversible. More work in, hotter gases coming out. The same principle over here. A lot of people had 4S, no problem. But every now and then, not too many had it kicked over that way. What would that have said about the entropy? It would have been destroyed. Yeah, that can't happen. You need to have the entropy out that way, so it kicks over like this, and there's 4 actual. So there you go. That makes sense? And then you take a look. What about the temperature 4 actual compared to temperature 4 isentropic? Which one's higher? The actual, meaning you got less work out of that gas stream in the turbine than you could have if it would have been isentropic expansion. Well, you play a lot of games like this. I think they're helpful. If I just say, let's focus on this compressor for a minute. If the compressor has a given isentropic efficiency, just pick one and then say, oh, what's going to happen to it? Maybe it increases, maybe it decreases. For this problem, the isentropic efficiency is going to go up. Is this good or bad if it goes from 80 to 85? That's good. So we kind of get a sense, oh, that's good. You have improved the efficiency of that turbine or compressor. And then you just ask yourself different questions like, what happens to the temperature at state 2? What happens to the pressure, enthalpy, and entropy? Do they go up? You know, each one individually. First, do the pressure, temperature, enthalpy, entropy. Does it go up, down, or does it remain unchanged? Do you want to make a list like, okay, temperature, pressure, enthalpy, entropy, maybe stays the same, goes up, goes down? You know, can you solve that? And I'll walk around and take a look. So it's the compressor, and the isentropic efficiency of the compressor goes up. Think about going from 80 to 85%. What happens? So another way of answering this question is I'm really interested in what does the temperature at state 2 when I have isentropic efficiency of the compressor at 80%, how does it compare to the temperature at state 2 when I have an isentropic efficiency of 85%? You know, which one is greater, less, equal? That's what I'm trying to do, is I'm trying to compare that. The assumption is that the temperature at 1 is not going to change, and the pressure at 1 is not going to change. All we're doing is focusing on the temperature at 2 if I change the isentropic efficiency of that compressor. And here what happened was the isentropic efficiency improved. It went up from 80 to 85%. Those are just some numbers I picked. So a lot of us got this correct, right? What does that do? And maybe the temperature entropy diagram helps. Here is the low pressure, here's the high pressure, here is state 1. We're not going to change state 1. And here would be 2s, but we're moving to 2 actual with 80% isentropic efficiency. But if you move it to 85%, it's improving. Which way does it shift it? Yeah, I should have put dashed line on this one, because the dashed line indicates the presence of irreversibilities. So this would be going from 80 to 85%, going more toward 100% isentropic efficiency. So the T2 goes down. That's right. How about the pressure at 2 stays the same, unchanged? So let's say it's just unchanged. Okay, the enthalpy at 2. Yeah, this is one of those where H is a function of T only for a true ideal gas, and so it's proportional to. So our model would be something like H is equal to H reference, REF, some reference, yeah, plus C sub P T minus T reference. So if temperature goes up, enthalpy goes up. It's linear related with a constant specific heat. So if T, so this goes down. So maybe I write it like this. Temperature 2 goes down, pressure 2 remains unchanged, enthalpy 2 goes down, and the entropy at 2 goes down. True? Yeah. So you can see that the entropy is going to nudge closer to just be S1. Make sense? You get good at that game, and do it for the turbine. I mean, this never ends, right? But in the interest of time, let me just close out. One thing, I strongly encourage you, if you haven't seen a video describing how gas turbines work, go look. They're excellent. It's a marvelous piece of engineering, creativity. And they're very important in our modern society. Next time, we'll move into regeneration, reheat, and intercooling. 2 of these 3 enhancements to the efficiency of the cycle you've seen before. Which two of these three enhancements have you seen before for the vapor power cycle? Regeneration and reheat. Do you think they're kind of motivated by the same principle that we motivated in the vapor power? Yeah, the same type of system. So please look ahead, read ahead, and watch a few videos. Thank you for your attention.